Have you noticed that days feel shorter? Not because you're busier, not because life is moving fast, but because the day itself is actually shorter. Scientists confirmed it. Earth is spinning faster than it has in decades. The clocks we built to track time, they don't match the planet anymore. We're about to travel through melting ice caps, shifting molten iron miles beneath your feet, and forces so powerful they're physically pulling the ground you stand on. A planet secretly accelerating, and nobody warned you. If you enjoy what's coming, hit like and subscribe. You won't want to miss where this goes. Take a breath. We're going in. The atomic clock noticed before anyone else did. Not a human. Not a scientist staring at a screen. A machine, ticking in a basement lab in Colorado, counting time so precisely it wouldn't lose a single second in 300 million years. And one day, it flagged something strange. The planet had finished a full rotation too early. Not by hours, not even by minutes, by milliseconds. But that's the thing about precision. A millisecond to a machine is like a warning siren. Something shifted. Here's what confirmed science tells us. Earth is not a perfectly steady spinning top. It never was. The rotation speed changes. It wobbles, slows, speeds up. Scientists have tracked this for decades, but recently something new started happening. The planet began spinning faster than it had in at least 50 years of recorded atomic timekeeping. In 2020, Earth set the record for the shortest day since scientists began measuring with atomic clocks. Then, it broke that record again and again. The fastest day ever recorded happened on June 29th, 2022. Earth completed one full rotation, 1.59 milliseconds faster than the standard 24 hours. That sounds like nothing, but to the systems that keep your phone synced, your GPS accurate, your financial markets time-stamped, it matters enormously. Think of it like this. Imagine you set a timer for 60 seconds, but the minute ends at 58. Every single day, your whole schedule would slowly drift. Now scale that up to satellites, global communications, and internet infrastructure. The drift adds up, so timekeepers around the world had a quiet, serious meeting. They started discussing something called a negative leap second, which would mean deleting a second from our clocks entirely to keep up with the faster spinning planet. That has never been done in history. We've added leap seconds before to slow our clocks down, never to speed them up. And that moment, that conversation, told scientists something important. This acceleration wasn't just a blip, but what's actually causing it. That's where it gets strange, because there isn't one answer. There are several, and each one connects to a force you'd never expect to have anything to do with how fast your day moves. The leading confirmed theories point to things happening deep inside the planet, high up in the atmosphere, and locked inside the ice sheets, sitting at both ends of Earth. All of them pushing and pulling on the rotation at once, like invisible hands reaching in from different directions, each adjusting the speed without telling the others. We're going to follow every one of those hands, and what we find is stranger than most people ever imagine. We'll start underground. Miles beneath your feet, there is something moving that most people don't even think about. A liquid ocean of iron and nickel, slowly churning in total darkness at temperatures that would vaporize any machine we've ever built. And what scientists discovered about what it's doing to our rotation, nobody predicted. You can't see it, you can't feel it, but right now, miles below where you're standing, something is moving, not slowly, the way continents drift across millions of years, faster than that. A rolling, churning mass of liquid iron and nickel, hot enough to vaporize anything we've ever built, flowing in massive currents deep inside the planet. This is Earth's outer core, and scientists have confirmed it is not sitting still. The outer core starts about 1,800 miles beneath the surface. That's deeper than the entire width of the continental United States, from coast to coast. Down there, pressure is so extreme that iron, which is solid on the surface, turns into liquid. It moves, it swirls, and those swirling currents generate something we rely on every single day, Earth's magnetic field. But here's what scientists recently discovered that nobody expected. The movement of this liquid iron doesn't just create the magnetic field. It also affects how fast the planet spins. Here's the confirmed science. The outer core and the solid mantle above it are not perfectly locked together. They can slide past each other, even slightly. When the core slows down relative to the mantle and the surface you live on speeds up, like two gears shifting against each other. One slows, the other compensates. This is called core-mantle coupling. And researchers studying seismic data, which is vibrations through the Earth from earthquakes, have found evidence that shifts in the core's flow patterns correlate with changes in Earth's rotation speed over decades. This isn't a theory. It's a confirmed, observed relationship. What's harder to confirm is exactly why those core currents are shifting right now. That part is still being studied. Some researchers believe the patterns are cyclical, moving on a scale of roughly 60 to 70 years. If that's true, we may be entering a phase that speeds up rotation for years to come. Think about what that means. A force 2,000 miles underground, completely invisible, unreachable by any drill ever built, is nudging the clock of every living day on the surface. That feels like something out of a story, but this is confirmed planetary science. And this isn't the only force acting on Earth's spin from the inside. There's also something happening at the boundary between the outer core and the solid inner core, buried even deeper. Scientists recently detected that the inner core, a solid iron ball roughly the size of the Moon, may have started rotating at a different speed than the rest of the planet. Some research, still debated, suggests it may have even begun slowly moving in the opposite direction. If that's accurate, the implications for understanding Earth's future rotation go much further than anyone expected. But the inside of the planet is just one part of this. The surface is changing too, and the change happening at the top of the world, in the Arctic and Antarctic, is doing something to Earth's spin that is disturbingly measurable. That's where we go next. Picture a spinning figure skater. Arms stretched wide, they rotate slowly. Then they pull their arms in, tight against their body, and suddenly they spin faster. No extra push, no extra energy, just mass moving closer to the center. That's physics. That's what scientists call conservation of angular momentum. Now, picture Earth doing the same thing, involuntarily. This is confirmed science. When ice melts at the poles, massive amounts of water that were locked in place, sitting on land at the very top and bottom of the planet, flow into the oceans and redistribute toward the equator. Mass moves away from the poles and toward the middle. Slightly, but at the scale of trillions of tons, slightly is enough. Glaciers in Greenland and Antarctica are losing ice at rates confirmed by satellite measurements. Greenland alone is shedding hundreds of billions of tons of ice every single year. That ice becomes water. That water moves into the oceans. And the ocean doesn't just sit there. It redistributes around the globe, pulling slightly more mass toward Earth's widest point. That outward shift of mass toward the equator should theoretically slow the rotation, like the skater throwing their arms back out. The planet getting wider at the middle, spinning a little more lazily. And here's where the paradox kicks in. Ice loss is happening. Mass is redistributing. And yet Earth is spinning faster, not slower. So either the ice effect isn't the dominant force right now, or something else is overwhelmingly overpowering it. Scientists believe both are true at once. Multiple forces are acting simultaneously, each pulling in different directions. And right now, the forces that speed up the rotation are winning. But this balance will shift. As ice loss accelerates over the coming decades, the redistribution effect will grow stronger. There's also a second ice effect that most people never hear about. When ice sits on land for thousands of years, its weight pushes the land down. Greenland's bedrock is actually pressed lower than it would be without the ice on top. As the ice disappears, the land slowly rebounds, rises back up. This process, called glacial isostatic adjustment, changes the shape of Earth very slightly, which also adjusts how mass is distributed, which also nudges the spin. Both confirmed processes, ice melt and land rebound, are happening right now at the same time. Scientists can measure them separately using satellites and GPS sensors placed directly on the bedrock. The data is clear. The forces are real. What remains an open scientific question is exactly how these long-term ice effects will interact with the short-term forces speeding Earth up today. Because there are more forces still, and some of them come not from below the surface or from the poles, but from something billions of people interact with every single day without realizing it. The atmosphere. It weighs more than you think, far more, and it moves in massive, organized patterns that are quietly but measurably pulling on the planet beneath it. The atmosphere doesn't feel heavy. You walk through it. You breathe it. It seems like nothing. But the atmosphere is a layer of gas roughly 60 miles thick, pressing down on every square inch of Earth's surface. Its total weight is about 11 quadrillion pounds. That number is almost impossible to picture. Stack every building ever built by every civilization in history. The atmosphere is heavier, and it moves, not randomly, in enormous, organized rivers of air that circle the planet at different speeds, at different heights, flowing east and west, climbing and descending through pressure systems the size of continents. And when the atmosphere shifts, when those rivers of air slow down or speed up, they push against the surface below. This is confirmed science, documented for decades. Atmospheric angular momentum is a real, measurable force. When strong wind patterns, like the jet streams circling the northern hemisphere, accelerate or shift direction, they transfer tiny amounts of force to the solid planet beneath. The surface pushes back, the rotation adjusts. Scientists have measured this. During strong El Niño events, massive shifts in atmospheric circulation can change the length of a day by fractions of a millisecond. During major storm seasons, when wind patterns reorganize across hemispheres, the effect shows up in the data. It works because of something simple. Air has mass. Moving mass carries momentum. When that momentum shifts, something has to absorb it. Earth's surface absorbs it. The rotation responds. Think of it like wind pushing a boat. One gust doesn't change much, but sustained pressure from one direction, over time, moves something enormous. Now, here's where it gets stranger. The atmosphere itself is changing. Warming temperatures are altering wind patterns. The jet streams are shifting. The distribution of air pressure around the planet is not what it was 50 years ago. And if the atmosphere was already capable of nudging Earth's rotation with its old circulation patterns, the new ones will do something different. What exactly? Scientists are still studying this. The modeling is complex. This falls in the category of a confirmed mechanism with an uncertain future impact. But there's another atmospheric effect that is much more direct, seasonal, predictable, and almost poetic in its simplicity. Every year, as summer arrives in the northern hemisphere, the atmosphere expands slightly as it warms. It becomes physically larger, pressing outward. As winter comes, it contracts. This breathing cycle of the atmosphere actually changes Earth's rotation slightly with the seasons. In winter, the planet spins fractionally faster. In summer, a hair slower. Your day is literally different lengths depending on the time of year, by amounts too small to feel, but large enough for precision instruments to record. And this is just the atmosphere. There are forces pulling on Earth's rotation from higher up still, from the sky. from something 239,000 miles away, pulling at the oceans with invisible gravity every single hour of every single day. What the moon is doing to Earth's spin is something most people were never taught, and the answer might genuinely surprise you. Every time you look at the ocean moving, waves rising, tides creeping up a beach, water pulling back to reveal wet sand, you are watching Earth slow down. Not fast, agonizingly, slowly. But it's real, it's confirmed, and it has been happening for 4.5 billion years. Here's the mechanism. The moon's gravity pulls on Earth, specifically on the oceans. Water bulges toward the moon slightly on the side facing it, and slightly on the opposite side too, due to the way gravity and momentum interact. These bulges are the tides, but Earth is rotating faster than the moon is orbiting, so the tidal bulges get pulled slightly ahead of where they'd be if Earth were spinning at the same speed as the moon moves. The moon pulls backward on those bulges, like grabbing a spinning top from the edge. That pull creates a friction effect. It drains a tiny amount of rotational energy from Earth, and that energy doesn't disappear. It gets transferred to the moon, which very slowly pushes the moon outward into a higher orbit. This is confirmed, completely documented. Laser reflectors left on the lunar surface by astronauts allow scientists to measure the moon's distance precisely. The moon moves about 1.5 inches farther away from Earth every year, and as it does, Earth's rotation slows correspondingly. How much has Earth slowed because of this over billions of years? When the first single-celled life appeared on Earth, a day was about 16 hours long. The moon was much closer. It's been pulling the brakes ever since. This long-term tidal braking is the dominant force behind Earth's slowing over geological time. On a scale of millions of years, Earth is spinning down. Eventually, in billions of years, Earth's rotation could slow enough that one side always faces the moon. Just like the moon always shows us the same face, tidally locked, frozen. But here's the twist in this story. On the short timescale of decades and centuries, tidal braking is real, but relatively small compared to the other forces in play right now. The atmosphere, the core, the ice, these are currently overpowering the moon's braking effect. That's why Earth has been speeding up recently, even though the moon is still slowing it down over longer stretches of time. Multiple forces, pulling in opposite directions. And right now, the speeders are winning. There's one more piece of this moon connection that most people never hear about, something called polar wander. As the distribution of mass on Earth slowly shifts, from ice moving to ocean, from land rising, the physical spin axis of the planet shifts too. The point around which Earth rotates is not fixed. It drifts. This drift is measurable, and in recent decades, scientists confirmed it has changed direction. Where the pole was drifting before, it is now drifting differently. The cause? Partly the ice loss, partly the water redistribution. The very act of melting is nudging which direction Earth's axis tilts as it spins. That's the planet physically reorganizing itself around a moving center. And what's happening at the center, deep inside, is about to get much stranger than anything we've covered so far. For a long time, scientists assumed the center of Earth was simple. A solid iron ball, dense, hot, locked in place by unimaginable pressure, sitting perfectly still at the very middle of the planet while everything else spun around it. That assumption was wrong. In 2023, a study published in the journal Nature Geoscience sent shockwaves through the scientific community. Researchers analyzed seismic wave data, vibrations from earthquakes that travel all the way through the planet, and compared recordings spanning several decades. What they found was alarming in its simplicity. The inner core had slowed down, not stopped completely, but the solid iron ball at the center of the planet, which had been rotating slightly faster than the rest of Earth for years, appeared to have decelerated. Some of the data suggested it had essentially matched the rotation of the outer layers. Some interpretations of the data suggested it had begun rotating slightly backward. This is still being debated. It is a scientific mystery in real time. Other researchers have challenged parts of the interpretation, but the core observation that seismic waves passing through the inner core are arriving differently than they did decades ago, suggesting a change in how the core is oriented or rotating, is confirmed by multiple independent research teams. The inner core is a solid ball about the size of the Moon, buried 4,000 miles beneath the surface. Nothing about it is accessible. Scientists can't drill there. They can't send instruments. The only way they can see inside is through earthquake vibrations, and those vibrations are telling them something moved. Here's why this matters for rotation. The inner core, the outer liquid core, the mantle, and the surface crust don't all spin as one locked system. They interact through friction, magnetic forces, and gravitational coupling. If the inner core shifts its rotation, speeds up, slows, or reverses, it exchanges angular momentum with the layers around it. A change deep inside can ripple upward. It can affect how fast the planet spins at the surface, not instantly, not dramatically, but measurably, over years and decades. Think of it as a spinning gyroscope with a separate weight inside that can roll around freely. Shift the inner weight, and the whole gyroscope responds differently. What started this change in the inner core? That part is genuinely unknown. Some researchers connect it to the same 60 to 70 year cycle seen in core mantle coupling. Others think it relates to pressure changes from the outer core's fluid dynamics. It may be entirely natural, part of a rhythm Earth has been running through for millions of years without us ever having the tools to notice. Or it might be something else, something we haven't fully characterized yet. The honestly humbling part of all this is that the center of your own planet is still a mystery. We've mapped the surface of the Moon in more detail than we've mapped the inside of Earth, and in between that iron core and your feet, there is a layer that most people have never heard of, one that is moving in ways that suggest Earth has been building up to something for a very long time. Between the churning liquid iron of the outer core and the thin rocky crust you walk on, there is a layer 3 times thicker than the distance from New York to Los Angeles. Solid, but not rigid. Rock that, under enough heat and pressure, over enough time, flows like an extremely slow liquid. This is the mantle. And it is moving. Not fast. Not even close to fast by any human standard. Parts of it move about as quickly as your fingernails grow, a few inches per year. But it is vast, and it carries enormous mass, and over millions of years, its movements reshape everything above it. Here's what's confirmed. The mantle isn't uniform. It has hotter, softer regions where material rises slowly toward the surface, like lazy bubbles in thick syrup. It has cooler, denser regions where old ocean crust that sank back into the planet sits, heavy and sluggish, pulling downward. These convection currents, rising hot material, sinking cold material, are what drives tectonic plates across the surface. Continents move because the mantle under them is moving, but the mantle also interacts directly with the planet's rotation. When massive amounts of material shift position deep inside, the distribution of Earth's mass changes. And when mass distribution changes, the spin changes. This is the same physics as the ice melt. Mass moving to a different location alters how fast the planet rotates around its axis. Mantle convection is far too slow to cause the changes scientists are measuring on timescales of years or decades. That's confirmed. But on timescales of thousands to millions of years, it is one of the dominant forces reshaping how Earth spins. There's something more immediate happening in the mantle though. Something geologists have been watching with increasing interest. In recent decades, seismic imaging, essentially creating 3-dimensional pictures of the inside of Earth using earthquake data, has revealed enormous anomalies in the mantle. Two massive structures, each roughly the size of a continent, sit near the core mantle boundary on opposite sides of the planet, one beneath Africa and one beneath the Pacific Ocean. They are denser than the surrounding mantle, hotter, compositionally different. Scientists call them large low shear velocity provinces. The name is a mouthful. What matters is that they're real, they're enormous, and their role in Earth's dynamics isn't fully understood. Some researchers believe they influence where mantle convection flows. Others think they anchor or disrupt the patterns of the liquid outer core above them, which connects back to the magnetic field and the rotation. They have been there for hundreds of millions of years, surviving continent collisions and mass extinctions. Whether these ancient buried structures are doing anything to Earth's current rotation speed is unknown. It's an open question in planetary science. But here's what ties all of this together. Every layer of this planet, the inner core, the outer core, the mantle, the crust, the oceans, the atmosphere, is in motion. They all interact, pull on each other, transfer momentum back and forth. Earth's rotation is not controlled by one thing. It is the result of every one of these systems pushing and pulling simultaneously. And humans recently added themselves to that equation. What civilization has done to the planet's mass distribution is measurable, and it points somewhere unexpected. Nobody planned this, nobody intended it, but the things humans have built, pumped, and moved around the surface of this planet over the last century have physically changed how it rotates. This is confirmed science, published in peer-reviewed research, and the scale of it is genuinely startling. Start with water. Over the 20th century, humans extracted enormous amounts of groundwater from aquifers beneath continents, underground reservoirs that had stored water for thousands of years. That water was used for agriculture, cities, industry, and most of it eventually evaporated or flowed into the ocean. A study published in 2023 calculated that between 2016 and 2021, human extraction of groundwater shifted enough mass from underground reservoirs to the ocean that it measurably changed Earth's rotational axis. The planet tilted very slightly because of where we moved water. Not a metaphor. The physical pole drifted by about 31 inches to the east, partly attributable to groundwater depletion, shifting mass toward the equatorial oceans. This is the same mechanism as glacier melt, mass moving from one location to another, except this time, humans caused it directly by pumping water out of the ground. And that's not the only human contribution. The building of large reservoirs has the opposite effect. When water is held back behind a dam in mountainous or mid-latitude regions, mass that would have flowed to the ocean is kept inland. The Hoover Dam, the Three Gorges Dam in China, and thousands of other reservoirs around the world collectively hold back trillions of gallons of water. Keeping that mass closer to the poles, fractionally, affects rotation in the opposite direction from groundwater depletion. The net effect of all human water management on Earth's rotation is small compared to natural forces, but it is measurable, it is real, and it is accelerating as human water use grows. Researchers have also looked at changes in land use, deforestation, urbanization, agriculture, and their effects on how soil moisture and carbon storage are distributed. These are more speculative in terms of rotational impact, still being studied. But the pattern is clear. Human activity at scale is not neutral. It has a physical signature on the planet. There's something deeply strange about sitting with that fact. The rotation of Earth, a force we think of as ancient, geological, cosmic, is being slightly nudged by irrigation systems and concrete reservoirs and water pumps. It raises an uncomfortable question. If humans can inadvertently shift Earth's rotation through water management, what else are we changing without realizing it? And as those changes add up over decades, do they interact with the natural forces we've already discussed? The core, the ice, the atmosphere, in ways we haven't fully mapped? That question doesn't have a clean answer yet. But scientists are building better models every year, and the next piece of this story connects all of these forces to something you can actually see and feel. A wobble. A real, physical wobble in the way Earth spins on its axis. One that completes itself every 14 months, and one that is shifting in ways scientists are still trying to fully explain. Earth doesn't spin perfectly upright. It doesn't spin perfectly steady. It wobbles. This is confirmed, measured, and given a name. The Chandler Wobble. Discovered by American astronomer Seth Carlo Chandler in 1891, it describes a small, irregular oscillation in Earth's spin axis, the imaginary line running pole to pole around which the planet rotates. The wobble causes the geographic North Pole to trace a rough circle about 30 feet wide over a period of roughly 14 months. 30 feet, not miles, not thousands of miles, 30 feet. And yet this tiny wobble has been tracked by scientists for over a century, and it shows up clearly in the data. For most of that time, the wobble was stable, predictable. It completed its roughly 14-month cycle and repeated. Astronomers knew what to expect. Then something strange happened. In around 2000, the Chandler Wobble slowed significantly. It nearly stopped for a period of a few years. This was unusual enough that scientists paid close attention. Various explanations were proposed: changes in ocean pressure, atmospheric shifts, groundwater movement. Most researchers concluded it was a combination of natural factors. The wobble resumed. But more recently, the direction of the wobble has shifted. NASA data confirmed in 2021 that Earth's rotation axis and the wobble around it had drifted toward the east. The speed of that drift increased around 2000. The suspected causes were ice loss from Greenland and groundwater depletion. The same forces we've already talked about. This matters because the spin axis is not just a mathematical concept. The actual physical poles, north and south, are slowly moving across the planet's surface because of it. If the drift continued at its current rate and direction for many thousands of years, it would meaningfully change which parts of the planet face different angles of incoming solar radiation. That's not happening on any timescale that affects your life, but it illustrates how interconnected all of these forces are. Change the ice, change the groundwater, the poles move, the wobble shifts, the rotation responds. Here's the part that makes scientists genuinely uneasy. The Chandler Wobble's natural period, 14 months, is determined by Earth's internal structure. The way mass is distributed inside the planet sets the rhythm. If that internal distribution changes significantly through mantle movement, core shifts, or mass redistribution from human activity, the wobble itself could change its period. Confirming that would require very precise, long-term measurements. And scientists are making them. So far, the 14-month cycle holds, but the direction and amplitude of the wobble continue to evolve in ways being actively studied. There is something almost eerie about all of this. A 30-foot wobble in the axis of an 8,000-mile-wide planet, invisible to every human on the surface, slowly shifting because of melting glaciers, pumped groundwater, and movements 2,000 miles underground. Every force we've talked about, the core, the ice, the atmosphere, the moon, human water use, they all leave fingerprints on this wobble, and they all connect to something that's been quietly happening at the South Pole that most news coverage hasn't fully explained. Something that researchers are watching very carefully. Something that, if it continues, could eventually change how fast every single day moves for every person alive. Antarctica is not just cold, it is a continent, a landmass, buried under ice that in some places reaches nearly 3 miles thick. And beneath all of that ice, buried deep, is terrain, mountains, valleys, lakes, and plains. that most humans have never seen, and most maps don't show in detail. Scientists are studying this hidden landscape for one specific reason. It is changing, and the way it is changing will affect Earth's rotation in ways that won't fully show up for decades. Here's the confirmed picture. The West Antarctic ice sheet, the portion of Antarctica that sits on ground mostly below sea level, is losing ice faster than any other part of the continent. Satellites measure its mass continuously. The numbers are clear. This ice sheet lost about 150 billion tons of ice per year on average during the 2010s. That rate is accelerating. When this ice melts, the water enters the ocean. Mass moves from a polar region very close to the spin axis toward the equatorial oceans, which are farther from the axis. As we've covered, this redistribution should theoretically slow Earth's rotation slightly over time. But there's a second process happening underneath this ice that almost nobody talks about. Beneath parts of the West Antarctic ice sheet, there are lakes, not on the surface, below the ice, formed by geothermal heat from the bedrock. Lakes of liquid fresh water, sitting in the dark under miles of frozen ice, completely cut off from the surface. Scientists have identified over 400 of them beneath the Antarctic ice. Some of these lakes are connected. Water flows between them through subglacial rivers, rivers that exist in total darkness, under crushing pressure, flowing between liquid pockets beneath one of the most hostile surfaces on Earth. These lakes act like lubricant. When they drain or fill, the ice sheet above them can slide more easily or more slowly across the bedrock. That affects how fast the surface ice moves toward the coast. It influences where and how quickly ice breaks off into the ocean. This is confirmed science. Satellite measurements and ice-penetrating radar have mapped many of these lakes. The dynamics of how they affect ice flow is an active field of research. What this means for rotation is indirect but real. Faster ice movement means faster mass loss to the ocean, faster mass redistribution, a more rapid shift in how Earth's weight is balanced. The subglacial lakes are part of the machinery driving how quickly that happens. And underneath the ice, there is something else. The bedrock of West Antarctica sits in a bowl, edges higher than the center. As ice melts from the outside in, ocean water can eventually flow inland under the remaining ice, accelerating the collapse. Researchers call this a potential instability threshold, a point beyond which the retreat becomes essentially irreversible on any human timescale. If that threshold is crossed, the effect on ocean distribution and Earth's rotational balance would be substantial and lasting. What you just heard covers only the western side of the continent. The eastern ice sheet is larger, more stable for now, but warming is reaching it too. What's been discovered beneath it goes further than almost anyone expected, and that discovery changes how scientists think about the future of every single day on this planet. For decades, scientists pointed to West Antarctica and said, "That's the unstable one. That's the one to watch." East Antarctica, they said, is a fortress. Thick, cold, ancient, locked in place by its own mass and the extreme temperatures above it. That picture is changing. East Antarctica holds more ice than anywhere else on Earth. If it melted completely, which is not happening soon, sea levels would rise by roughly 170 feet. The entire Florida coastline would vanish, most of Bangladesh, enormous stretches of every coastal nation on the planet. Nobody expected it to be destabilizing this early, but in 2022, satellite data confirmed something that alarmed researchers. The Conger Ice Shelf, a floating platform of ice roughly the size of Rome attached to the East Antarctic coast, collapsed entirely in a matter of days. Gone. An ice structure that had existed for thousands of years disintegrated in less than a week. This is confirmed. It happened. And it was the largest ice shelf collapse ever recorded in East Antarctica. Ice shelves are important because they act as buttresses. They don't sit on land, they float on the ocean, but they hold back the glaciers behind them. When an ice shelf collapses, the glaciers it was restraining can accelerate toward the sea. The ice doesn't disappear immediately, but the break is gone. For Earth's rotation, this matters for the same reason West Antarctic ice loss matters. Mass that was sitting near the spin axis at the bottom of the planet moves into the ocean and redistributes outward. The more East Antarctic ice that eventually enters the ocean, the greater the long-term effect on rotation. But researchers found something else beneath East Antarctica that shifted the conversation entirely. Using airborne radar that can see through miles of ice, they mapped the terrain underneath. What they found was a network of valleys, basins, and channels carved deep into the bedrock, some of them sitting well below sea level, connected to the ocean. This means ocean water can potentially reach the base of East Antarctic glaciers through submerged pathways. Warm ocean water, if it finds those channels, can melt the ice from underneath, from the bottom up, invisibly, without any change visible on the surface. This is a confirmed geographic reality. Whether warm water is actively flowing through those channels right now is still being studied. It is a known risk, not yet a confirmed event. Scientists are watching it closely. What it means is that East Antarctica, the fortress, the stable one, the one that wasn't supposed to be part of this story yet, may be more vulnerable than anyone believed, and the forces destabilizing it are not coming from above. They're coming from the ocean, from warming water circulating in currents that have been shifting for decades. Currents that, it turns out, are themselves being reorganized by changes in Earth's rotation. The planet is feeding back on itself. Rotation changes affect the oceans. Ocean changes affect the ice. Ice changes affect the rotation. A loop, and something else is accelerating that loop from an angle nobody saw coming. The ocean is not a still pool. It is a moving system, a global conveyor belt of water that carries heat from the tropics toward the poles, cold water from the depths back toward the surface, and salt across thousands of miles of open sea. This conveyor, scientists call it the thermohaline circulation, is one of the most important climate systems on Earth. It regulates temperature across entire continents. Without it, Northern Europe would be dramatically colder. The Amazon would receive less rainfall. Ocean ecosystems from the surface to the deep would be fundamentally different, and Earth's rotation helps drive it. This is confirmed physics. As Earth spins, it deflects moving water and moving air to the right in the northern hemisphere and to the left in the southern hemisphere. This is called the Coriolis effect. It's the reason hurricanes spin counterclockwise in the north and clockwise in the south. It's the reason ocean gyres, enormous circular current systems, rotate the directions they do. The spin of the planet is physically shaping how every drop of ocean water moves, so when Earth's rotation speed changes, even by milliseconds, it subtly adjusts the Coriolis effect. The deflection of moving water shifts, fractionally. Over time, those fractional shifts accumulate. Current patterns that took centuries to establish begin to respond. Scientists have confirmed that the Atlantic thermohaline circulation has slowed significantly over the past century. Studies using sediment records and oceanographic measurements put it at its weakest point in over 1,000 years. The cause is a mix of factors: fresh water from melting ice, diluting the salty water that drives the sinking, warming temperatures, reducing temperature contrasts that fuel the flow. Whether the tiny changes in Earth's rotation are contributing to this slowdown is still being studied. The rotation effect on ocean circulation is real but considered small compared to temperature and salinity changes. It is a confirmed mechanism with an uncertain magnitude. But here's what is not uncertain. If the thermohaline circulation weakens significantly or collapses, which some researchers consider a genuine risk within this century, the redistribution of ocean heat around the planet would change dramatically. Ocean mass would shift, temperatures at the poles would change, ice melt patterns would change, and every one of those changes feeds back into the rotation. Think about that loop again. Rotation affects ocean currents. Ocean currents affect ice melt. Ice melt affects mass distribution. Mass distribution affects rotation. One system pulling on the next, in a circle. What happens when one part of that loop accelerates? Scientists are building models to find out. The answers are not settled, but the models consistently show that the interactions between these systems are stronger than previously thought. And there is one more ocean rotation interaction that is direct, measurable, and happening right now. The weight of ocean water pressing on the seafloor flexes the crust beneath it. As sea levels rise and water redistributes, that pressure changes. The solid rock of the ocean floor is being pushed slightly differently than it was a century ago. Rock that flexes is rock that changes shape, and a planet that changes shape spins differently. But before we get to what's happening to the crust itself, there's something in the sky that's been pulling on Earth's rotation for billions of years and is only now being measured precisely enough to understand. Something that started not at Earth's surface, not underground, but in space, in the way this planet was born. To understand why Earth's rotation is changing, it helps to understand where that rotation came from. 4.5 billion years ago, there was no Earth. There was a cloud of gas and dust slowly collapsing under its own gravity, the early solar system condensing into the bodies we know today. That cloud was not perfectly still. It had a slight rotation, a slow collective spin inherited from the angular momentum of the gas that formed it. As the cloud collapsed inward, that rotation accelerated. Just like the figure skater pulling their arms in, the shrinking cloud spun faster. The material clumped together. Collisions happened, enormous. Violent collisions between rocks, ice, and gas. And each collision transferred momentum. Some collisions slowed things down. Some sped them up. The net result, after millions of years of chaos, was a proto-Earth spinning at a rate that scientists have calculated would have given it a day of roughly 6 hours. Then something hit it. This is the confirmed scientific model, the giant impact hypothesis. A body roughly the size of Mars, which scientists have named Theia, collided with the young Earth in a catastrophic impact. The collision was not a head-on crash. It was a glancing blow, and that angle mattered enormously. The impact blasted enormous amounts of material into orbit. That material eventually coalesced into the Moon, but the collision also dramatically altered Earth's rotation. The glancing impact added angular momentum, changing the tilt of Earth's axis and altering its spin rate. Without that impact, Earth might spin differently today. Its axis might be tilted differently, or not at all. The seasons might not exist as we know them. The Moon might not exist at all. So, the spin you feel in every sunrise and every sunset, the rhythm of day and night that every living thing on this planet has evolved around, began with a catastrophic collision 4.5 billion years ago. Since that collision, Earth has been slowly losing rotational energy. Tidal braking from the Moon, as discussed earlier, has been pulling the brakes for billions of years, and over geological time, other forces have pushed and pulled. Asteroid impacts, adding or subtracting momentum, massive volcanic eruptions, redistributing mass, the continents, drifting and reshaping the planet's moment of inertia. Every major event in Earth's history left a fingerprint on its rotation speed. The largest volcanic event in the last 66 million years, which buried half a continent in lava, slightly changed Earth's mass distribution. The asteroid impact that ended the age of large dinosaurs, confirmed science, would have sent shockwaves through the planet and shifted its rotation measurably, though by how much is still being calculated. Earth's rotation has never been a fixed constant. It has always been a running record of everything that has ever happened to this planet, and what's happening to it right now is being written into that record in real time. But there's a piece of this story that connects the ancient past to the present in a way that most people have never heard. Something that happened during the last ice age is still affecting how fast the planet spins today, and will continue to do so for thousands of years. The last ice age ended roughly 11,000 years ago. The glaciers retreated, sea levels rose, the megafauna that had lived alongside them went extinct one by one, and human civilization began to emerge in the warmer, more stable world that followed. But the planet didn't finish adjusting. When ice sheets up to 2 miles thick sat on top of North America, Scandinavia, and parts of northern Asia for tens of thousands of years, they pushed the land down. Not a little. In some places, the weight depressed the bedrock by hundreds of feet. The crust of the planet was bent under the load. When the ice melted, the load disappeared, and the land began to rise, slowly, incrementally, in a process that is still happening right now, 11,000 years after the ice left. This is called post-glacial rebound, and it is confirmed, measured, and ongoing. In Scandinavia, the land is rising by about 1 inch per year, fast enough to be measurable not just by satellites, but by ancient shoreline records showing where the ocean used to reach that is now dry land sitting well above sea level. Parts of northern Canada are rising at similar rates. The crust is still bouncing back from ice that melted thousands of years ago. This rebound matters for Earth's rotation because it is redistributing mass. As land rises in formerly glaciated regions, mass that was spread horizontally under the ice is now moving upward and concentrating differently. The shape of the planet is subtly changing, and as the shape changes, the moment of inertia changes, the spin adjusts. Post-glacial rebound is confirmed to have a measurable effect on Earth's rotation rate. Scientists have calculated that this ancient process is contributing to a gradual, long-term slowing of the planet's spin, moving mass away from the equator and upward toward the poles, which has the opposite effect of melting ice. It is another force pulling in a different direction from everything else. Here's what makes this particularly striking. The ice that caused this rebound is gone. The humans who watched it melt didn't have writing. They didn't have cities. And yet, what they witnessed is still physically reshaping the planet today, still nudging the rotation, still slowly pushing land skyward in Canada and Finland. The past doesn't finish, it just slows down. And there's a future version of this story already being written. The ice that is melting right now, from Greenland, from Antarctica, from mountain glaciers around the world, will trigger its own rebound. The land underneath current ice sheets will begin to rise as the weight leaves. That process will take thousands of years to fully play out. Humanity will not be around in its current form when that rebound finishes, but it will finish, and the rotation of Earth will record it. For now, the rebound from the last ice age and the redistribution from the current one are both active at the same time, pushing in partially opposite directions. Scientists can separate their contributions using detailed models. The data is consistent. Both signals are real. But underneath all of these surface and near-surface processes, something is happening that operates on a completely different scale. Something that ties Earth's rotation to the behavior of the entire solar system. And it starts with a force so subtle that it took centuries for astronomers to even measure it. Earth does not orbit the Sun in isolation. It shares the solar system with 7 other planets, each one massive enough to exert a gravitational pull on everything around it. Jupiter alone is more than 300 times the mass of Earth. Saturn is close behind. Even from hundreds of millions of miles away, these giants are pulling on Earth, not enough to throw it out of orbit, but enough to do something subtle and strange. They are changing the shape of Earth's orbit. Over long timescales, tens of thousands to hundreds of thousands of years, the gravitational interactions between planets cause Earth's orbital path to slowly stretch and compress. The orbit shifts from more circular to more elliptical and back again. The angle of Earth's axial tilt wobbles between about 22 and 25 degrees over a 26,000-year cycle. The timing of when Earth is closest to the Sun shifts over a cycle of about 100,000 years. These are called the Milankovitch cycles, named after the Serbian mathematician Milutin Milankovic, who worked out the math in the early 20th century. And they are confirmed to drive ice ages. When Earth's orbit and tilt align in ways that reduce summer sunlight reaching the northern hemisphere, where most of the land is, ice builds up. It reflects more sunlight, cooling the planet further. Ice ages begin. When the cycles shift and summer sunlight increases, ice melts. Interglacials begin. The ice age cycles that shaped the last million years of Earth's history were driven, in significant part, by the gravitational nudging of Jupiter and Saturn. Now, here's the direct connection to rotation. Ice ages change how much ice sits at the poles. As established, ice at the poles affects rotation through mass redistribution and post-glacial rebound. So, the gravitational pull of Jupiter, acting over tens of thousands of years through the mechanism of ice age cycles, is indirectly sculpting how fast Earth spins. This is confirmed science. The chain of causation is long, but every link in it is documented. What does this mean for the rotation changes happening right now on a timescale of decades? The planetary influences are far too slow and small to explain what atomic clocks are recording today. The recent acceleration is driven by the near-term forces, the core, the ice, the atmosphere, the humans. But the Milankovitch cycles set the background conditions. They determined how much ice built up over the last ice age, and therefore how much post-glacial rebound Earth is still experiencing. They determined where Earth sits in its long orbital rhythm right now. They are the stage on which all the faster processes are playing out. Understanding what Earth's rotation is doing today requires knowing where we are in these deep cycles. And where we are is unusual. The current interglacial, the warm period between ice ages we've been living in for 11,000 years, may be lasting longer than it otherwise would because of something humans have added to the atmosphere. That addition is changing the rotation story in ways the Milankovitch cycles never anticipated. And the most direct measurement of those changes is coming from a network of instruments that didn't exist a generation ago. Instruments that are now showing scientists something that keeps getting harder to explain. For most of history, scientists measured Earth's rotation the only way they could, by watching the sky, tracking stars, calculating how long it took for a specific point in the sky to return to the same position. Comparing those measurements to clocks, this was the method for centuries. It worked, but it had limits. The measurements were slow. They blended short-term variations with long-term trends. Small changes got lost in the noise. Then, satellites changed everything. Starting in the 1980s and accelerating through the 90s and 2000s, a global network of tracking stations began using a technique called Very Long Baseline Interferometry, where radio telescopes on opposite sides of the planet simultaneously receive signals from distant quasars, objects billions of light years away, and measure tiny differences in the arrival time of those signals. From those differences, scientists can calculate Earth's orientation and rotation speed to extraordinary precision. This is confirmed technology, currently used by space agencies around the world. It can detect changes in the length of a day down to a few tenths of a microsecond, a millionth of a second. Changes that would have been completely invisible to any previous generation of scientists. And what these instruments are seeing is a planet in constant, restless motion. The length of a day varies by fractions of a millisecond week to week, driven by atmospheric changes and ocean currents. It varies by slightly larger amounts season to season as the atmosphere breathes. It shows longer-term trends over years and decades, driven by the core, the ice, and the other forces already discussed. Every one of these signals is readable by scientists who know what to look for. Satellites also gave scientists the ability to track mass redistribution in real time. The GRACE mission, Gravity Recovery and Climate Experiment, used 2 spacecraft flying in precise formation to measure tiny variations in Earth's gravitational field. Where mass increased, the leading satellite would accelerate fractionally. By tracking those accelerations over time, scientists mapped where water was moving across the planet. GRACE and its successor, GRACE Follow-On, have confirmed ice loss in Greenland and Antarctica, groundwater depletion in aquifers, seasonal water storage in river basins, and the slow rise of land after glacial rebound, all from orbit, all without touching the ground. These are not theoretical. These are direct measurements of mass redistribution happening right now, and they feed directly into models of Earth's rotation, because every kilogram of mass that moves changes the planet's moment of inertia. The satellite era has given scientists the first truly global, continuous, high-precision view of a planet in motion, and the picture they're assembling is more dynamic than anyone expected 20 years ago. But precision brings its own unsettling gift. The more precisely you can measure, the more anomalies you find. In the rotation data collected over the last 2 decades, there are signals that the models don't fully explain, fluctuations that don't cleanly correspond to any known forcing, patterns that repeat but whose source hasn't been pinned down. Some of these anomalies might be measurement artifacts. Some might be interactions between known forces the models haven't captured yet, and some might be pointing to something that hasn't been identified. That last possibility is what keeps some researchers working late. And one of those unresolved signals connects to something happening at the boundary between the ocean floor and the mantle beneath it. A boundary that is far stranger than most people realize. Most people picture the bottom of the ocean as flat, still, and featureless, miles of dark water pressing down on mud. The reality is something else entirely. The ocean floor is geologically alive. It spreads apart at mid-ocean ridges, underwater mountain ranges, where magma rises from the mantle, cools, and forms new crust, pushing the existing seafloor outward like a slow conveyor belt. At subduction zones, that old crust dives back under the continents, sinking into the mantle, triggering earthquakes and fueling volcanoes above. This process, seafloor spreading and subduction, is confirmed plate tectonics. It has been operating for billions of years, and it is continuously redistributing mass beneath the ocean. When old, dense oceanic crust subducts, sinks back into the mantle, it takes water with it. Seawater is chemically bound into the minerals of the oceanic crust over millions of years as it sits on the seafloor. When that crust subducts, the water gets carried deep into the mantle, where heat and pressure release it. That water rises, lowers the melting point of the mantle rock above it, and triggers volcanic activity at the surface. This is the confirmed mechanism behind most of the world's volcanic arcs: the Pacific Ring of Fire, the Cascades in the American Northwest, the volcanoes of Japan, Indonesia, and South America. But here's the part that connects to rotation. The subducting crust is dense, very dense. As it sinks into the mantle, it carries mass downward and inward, toward the center of the planet. Mass moving inward, closer to Earth's rotation axis, should slightly speed up the spin. Mass moving outward, toward the surface and equator, should slow it. Subduction is constantly moving mass in both directions simultaneously at different places around the planet. The net effect on rotation at any given moment depends on where subduction is most active and what angle the sinking slabs are at. Scientists have calculated that subduction contributes a measurable long-term signal to Earth's rotation. Though smaller than glacial rebound or core mantle coupling on human timescales, what's less settled is how the rate of subduction has changed over geological time. and whether it's changing right now in ways that matter. The Ring of Fire has been notably active in the past 2 decades. Significant earthquakes in Chile, Japan, Sumatra, and Alaska each released energy that measurably shifted Earth's rotation, individually tiny, but collectively adding up in the long record. The 2011 earthquake off the coast of Japan, one of the most powerful ever recorded, shortened Earth's day by about 1.8 microseconds and shifted the planet's figure axis by about 6.5 inches. These are confirmed measurements. A single earthquake, lasting minutes, changed how fast the planet spins. Scale that across thousands of earthquakes per year, the continuous creep of tectonic plates, the slow sinking of massive slabs of old ocean floor, and the seafloor stops being a background feature. It becomes an active participant in the rotation story. And under some of those subducting slabs, scientists have found pockets of material that behave like liquid where no liquid should exist. Something strange is happening at the boundary between what we can explain and what we cannot. That boundary is closer to the surface than you might think. The solid ground beneath your feet is not as solid as it feels. At the surface, the crust seems permanent. Rock and soil, bedrock, the foundation of everything. But the crust is thinner, relative to Earth's size, than the skin of an apple. And underneath it, the upper mantle is not entirely rigid. In some places, it contains zones of partially melted rock, not fully liquid, but soft enough to flow over very long timescales. This zone is called the asthenosphere, and it allows the rigid tectonic plates above to slide and drift. The asthenosphere is not involved in Earth's day-to-day rotation changes at the speed scientists are currently measuring. It operates on too slow a timescale, but it is the mechanism that allows all the long-term mass redistribution to happen: post-glacial rebound, tectonic drift, the slow response of the crust to changing ice and water loads. What is happening on faster timescales, and what has been measurably affecting rotation, is something that occurs at the surface: the movement of water through the land itself. Not just the visible movement of rivers to the sea, the invisible movement of groundwater through aquifers, soil, and fractured rock. The seasonal expansion and contraction of water stored in mountain snowpack and river basins. The slow draining of wetlands. The filling of reservoirs. All of this water movement redistributes mass. And, because it happens at or near the surface, far from Earth's rotation axis compared to deep interior forces, its leverage on rotation is significant relative to its weight. Scientists have now built detailed models of what is called surface mass loading, the effect of all the water, ice, soil moisture, and ocean changes at the surface on Earth's rotation. These models are compared to the satellite measurements from GRACE and the rotation measurements from Very Long Baseline Interferometry. When the models match the data, it confirms that the accounting is right. When they don't match, when there's a gap between what the models predict and what the satellites see, it points to a missing source. In recent years, some of those gaps have narrowed as models improved, others remain. There are seasonal variations in the rotation data that are mostly explained by atmosphere and ocean. There are longer-term trends that are mostly explained by ice loss and post-glacial rebound. And there are shorter, irregular fluctuations that are harder to pin down. One candidate for some of those unexplained short-term fluctuations is hydrology, the movement of water through the land surface in ways that aren't fully captured in global models. Droughts shift where water sits. Floods temporarily pool mass in unusual locations. Large-scale irrigation moves water from underground to the surface and then to the atmosphere in patterns that change year to year. The planet is not a closed, smooth system. It is lumpy, irregular, and constantly being rearranged by weather, human activity, and geology all at once. What this means practically is that even with the best satellites and the most precise measurements ever made, Earth's rotation cannot be perfectly predicted more than a few weeks in advance. The systems driving it are too complex, too interconnected, and too sensitive to fluctuations that cannot be fully modeled in advance. That unpredictability matters more than most people realize. And for one specific human technology, it matters enormously. A technology that billions of people use every single day without knowing it depends on knowing exactly how fast Earth is spinning at any given moment. Every time you use navigation on your phone, something extraordinary is happening above your head. A constellation of satellites, at least 24 at any time, often more, is orbiting Earth at roughly 12,000 miles above the surface, each one broadcasting a precise timestamp and its own location. Your phone receives signals from several of them simultaneously and calculates, from the tiny differences in signal arrival time, exactly where you are. The math works out to accuracy within a few feet, sometimes less. This is confirmed technology. The Global Positioning System was built by the United States military. Similar systems exist for Russia, Europe, and China. Together, they form a global navigation infrastructure that almost everything modern depends on. Aviation, shipping, emergency services, financial transactions, scientific instruments, and every single one of these systems depends on knowing, with extreme precision, how fast Earth is rotating at any given moment. Here's why. The satellites are in orbit, but Earth is spinning beneath them. When your phone calculates your position, it has to account for the fact that the ground is moving. If the calculation assumes Earth is spinning at a slightly wrong speed, if the rotation data fed into the navigation system is even a tiny bit off, the position it calculates for you will be wrong, by fractions of an inch at small errors, by yards at larger ones. For most navigation, a few feet of error is acceptable. But for precision agriculture, which uses GPS to guide planting and harvesting equipment to within inches, errors matter. For landing aircraft on instrument approaches in low visibility, errors matter. For guiding autonomous vehicles, errors matter. For the timing systems that underpin financial trading, where transactions are time-stamped to microseconds to prevent fraud, even tiny timing errors have consequences. To keep GPS accurate, the agencies that run these systems continuously monitor Earth's rotation using the very long baseline interferometry network already discussed. They publish updated rotation parameters, called Earth orientation parameters, regularly, sometimes daily. Navigation satellites receive these updates and adjust their calculations. This is an ongoing, never-ending operation. Earth's rotation is not a fixed number that gets entered into a computer once. It is a continuously measured, continuously updated variable that has to be fed into systems around the world in near real time. Every time Earth speeds up or slows down, every time a storm system reorganizes the atmosphere, every time a glacier carves an iceberg, every time groundwater is pumped out of an aquifer, the rotation changes slightly. The GPS systems have to keep up. This is not a hypothetical concern. It is an operational reality that space agencies manage every day. The people maintaining these systems understand, better than almost anyone, that Earth's rotation is not a constant. It is a moving target, and the stakes of getting it wrong are growing as the systems that depend on precise timing become more deeply embedded in everything from power grids to autonomous vehicles to global finance. There is one other system that Earth's rotation directly controls, one that is older, simpler, and more fundamental than GPS, one that cannot be updated by satellite, one that every country in the world has to agree on. And the ongoing tension between that system and a planet that refuses to spin at a fixed rate is quietly becoming one of the more unusual scientific and political debates of the modern era. Time, as most people experience it, feels like a natural thing. Days and nights, clocks on the wall, schedules, the second hand sweeping around. But behind all of that is an agreement, a human decision about how to define time. And Earth's changing rotation is slowly pulling that agreement apart. Here is the problem in plain terms. There are two kinds of time. Atomic time is based on the vibrations of cesium atoms, extraordinarily stable, consistent to within a second over millions of years. Universal coordinated time, which is what your phone and computer use, is supposed to stay close to astronomical time, the actual rotation of Earth. The two should agree, but they don't. Not perfectly, because Earth doesn't spin at a constant rate. For decades, the solution was the leap second. When astronomical time drifted more than 9/10 of a second away from atomic time, timekeepers would add a second to clocks worldwide, usually at midnight on December 31st or June 30th. 27 leap seconds have been added since 1972. Earth's recent acceleration changed the calculation. Instead of needing to add a second to catch up, the planet is spinning fast enough that for the first time, timekeepers began discussing removing a second, a negative leap second, to keep the two timescales aligned. This has never been done, and the prospect of it alarmed engineers, technologists, and scientists worldwide. The concern is not philosophical, it is practical. Every leap second that has ever been added has caused software problems. Systems that weren't coded to handle the jump between 23 hours, 59 minutes, 59 seconds, and 23 hours, 59 minutes, 60 seconds have crashed, glitched, or behaved unpredictably. The internet giant Cloudflare experienced a major outage during a leap second in 2017. Reddit, Mozilla, and LinkedIn all reported issues during past events. A negative leap second, jumping backward, is expected to be even more disruptive because far less software has ever been designed or tested for it. In 2022, the international body that governs time measurement voted to eliminate the leap second entirely by 2035. Instead of correcting clocks every few years, atomic time and astronomical time will be allowed to drift apart, and corrections will only happen over longer intervals, possibly centuries. This is a confirmed decision. The leap second will be abolished. Humanity will officially stop trying to keep its clocks precisely synced to the actual rotation of Earth. Think about what that means. For the first time in history, human time will formally decouple from planetary time. The second, the unit that every clock on Earth ticks, will no longer be anchored to the spinning of the planet that created it. That decision was made, in large part, because Earth's rotation is too unpredictable, too variable, too difficult to keep up with. And that unpredictability is growing, not shrinking. Because the forces driving it, ice loss, atmospheric change, groundwater redistribution, core dynamics, are not stabilizing, they are accelerating. What the next 50 years of Earth's rotation will look like depends on how those forces evolve, and one of the biggest unknowns sits at the very edge of what science can currently model. A threshold that, once crossed, changes everything that comes after it. Scientists use the word threshold carefully. It means a point beyond which a system changes its behavior in a way that can't easily be reversed. A cliff edge. Once you go over, going back requires a completely different set of conditions. Conditions that may not exist for thousands of years or ever. Earth's climate system has several of these thresholds. Scientists call them tipping points, and the evidence is growing that some of them are closer than previously thought. The West Antarctic ice sheet is one. As covered earlier, its bedrock sits in a bowl. Once ocean water reaches far enough inland, the retreat accelerates on its own. The question is no longer whether warming will eventually destabilize it, but how fast. The Greenland ice sheet is another. Studies have calculated that if enough ice melts, the sheet's own elevation drops far enough that its surface reaches warmer air, accelerating the melt further. Another self-reinforcing loop, confirmed physics, uncertain timeline. The Amazon rainforest is a third. As it dries from deforestation and shifting rainfall, it releases less moisture into the atmosphere, triggering less rainfall, which triggers more drying. A forest that generates its own climate starts to lose that ability. Portions of the Amazon are already showing early signs of this transition. The trend is confirmed. Each of these tipping points connects to Earth's rotation. More ice lost means more mass redistributed to the oceans. A destabilized Amazon shifts atmospheric circulation. Everything feeds back into the system of forces pulling on the spin. But here's what makes tipping points especially difficult to navigate scientifically. They are often invisible until very close. The system looks stable, data looks normal, and then a threshold is crossed, and the change comes faster than the models predicted. This has happened repeatedly in Earth's past. The end of the last ice age was interrupted by periods where temperatures jumped several degrees within decades. The planet flipped states quickly when conditions aligned. The rotation record from those transitions, preserved in ancient sediments and coral records, shows corresponding rapid changes in spin rate. The planet's rotation followed the climate, shifting faster as mass redistributed rapidly. The honest scientific position is this: tipping points exist. Some are confirmed. Their exact thresholds are not fully known. What lies on the other side, in terms of Earth's rotation and climate, can be modeled but not predicted with certainty. What can be said with confidence is that the forces pushing toward those thresholds are currently stronger than at any point in recorded human history. The ice is moving faster. The atmosphere is carrying more energy. The ocean is warmer at depths that took centuries to heat. And there is a signal in Earth's rotation record from the last 50 years that doesn't fit neatly into any of the models. Something is happening that all the known forces added together don't fully account for. Scientists have a name for the gap. Closing it requires looking somewhere that seems, at first, completely unrelated to a spinning planet. When you have a model that explains most of what you see, but not all of it, the remainder tells you something. Scientists call this the residual. It's the gap between what the math predicts and what the instruments actually measure. In a perfect model with perfect data, the residual would be zero. In practice, it never is. Some residual is expected, from measurement error, from simplifications in the model, from forces too small to track individually. But some residuals are too large and too structured to be noise. They repeat, they trend. They have patterns that suggest a real, unaccounted for source. In Earth's rotation data, researchers have identified residuals in the decade-scale variations that existing models struggle to explain. The atmosphere, the oceans, the ice, the core, all accounted for, and still there is something left over. Not huge, not dramatic, but persistent and real enough that multiple independent research groups have noted it. Several hypotheses have been proposed. One involves the deep ocean. The bottom layers of the ocean, the abyssal circulation, are cold, dense, and move very slowly. They have been poorly measured compared to surface currents. Recent deep ocean monitoring campaigns have found that these bottom waters are warming faster than expected, and that their circulation patterns are shifting. If the abyssal ocean is reorganizing its mass distribution in ways not captured by current models, it could account for part of the residual. This is a current area of research. Confirmed warming of deep ocean layers, uncertain implications for rotation models. Another hypothesis involves the way the atmosphere responds to warming at the poles. As the Arctic warms faster than the rest of the planet, a confirmed trend called Arctic amplification, the temperature difference between the equator and poles shrinks. That drives a more wavy, less stable jet stream. A less stable jet stream means the atmospheric angular momentum signal becomes harder to model and may be contributing differently to Earth's spin than it did in previous decades. This is a confirmed physical mechanism with modeled but not yet fully verified rotational consequences. A third hypothesis is more speculative. Some researchers suggest that deep earthquakes, occurring hundreds of miles underground at the boundary between the mantle and outer core, may affect the coupling between the core and mantle in ways not captured by existing models. None of these hypotheses has been confirmed as the source of the residual. The honest answer is that something is contributing to Earth's rotation changes that scientists haven't fully pinned down yet. That uncertainty is not a failure of science, it is science working correctly. But the residual matters because of what it implies. If there is a source of rotational forcing that isn't in the models, then predictions of how Earth's spin will evolve over the coming decades are incomplete. Decisions about timekeeping, GPS, satellite orbital calculations, and long-term infrastructure planning are all being made with models that have a known gap. That gap is being worked on. New ocean sensors are being deployed, new seismic networks are being expanded, new satellite missions are being designed. The tools for closing the gap are being built. And while that work continues, the planet itself is offering one more piece of evidence that the system is changing in ways that go deeper than any single force. Evidence written not in data or satellites, but in something far older, something preserved in rock, before atomic clocks, before satellites, before any instrument humans ever built. Earth was keeping its own record. In the sediment layers of ancient seafloors, in the growth rings of fossilized coral, in the chemical signatures locked inside ancient cave formations, the planet has been writing down its own rotation history for hundreds of millions of years, and scientists have learned to read it. The most direct record comes from something called tidal rhythmites, layers of sediment deposited by tidal cycles in ancient shallow seas. Tides leave faint but regular laminations in fine sediment. Each layer corresponds to a tidal cycle. By counting the layers and identifying seasonal patterns within them, geologists can calculate how many days were in a year at the time those sediments were deposited. Because Earth's orbit around the Sun hasn't changed significantly, a year is still roughly the same length. But if there were more days in that year, each day was shorter, and the number of days per year in the ancient record tells scientists exactly how fast Earth was spinning at that time. The results are striking. Confirmed data from tidal rhythmites deposited roughly 620 million years ago shows that a year then contained about 420 days. Each day was about 21 hours long. Earth was spinning noticeably faster. Data from coral fossils is even more detailed. Corals grow daily and seasonal growth rings, similar to trees. By analyzing ancient coral preserved in limestone, researchers have counted the daily rings within yearly cycles and confirmed the day count. 400 million year old corals show roughly 400 days per year, days of about 22 hours. This is not theory. These are physical counts of preserved biological records, cross-checked against independent sediment data. The slowdown of Earth's rotation over hundreds of millions of years is documented in rock. The rate of slowdown is consistent with what tidal breaking models predict, about 1 to 2 milliseconds per century on average, with variations driven by ice ages, continental positions, and ocean geometry, all of which affect how strongly the Moon's tidal breaking operates at any given time. What the ancient record also shows is that Earth's rotation has survived enormous disruptions. The impact that ended the age of large dinosaurs, massive volcanic eruptions, rapid ice age cycles, continental collisions. Through all of it, the planet kept spinning. The rotation changed, sometimes quickly by geological standards, but it never stopped. That resilience is real, but it comes with context. The changes happening now are fast by geological standards. The rate of ice loss, atmospheric change, and mass redistribution currently underway is happening on a timescale of decades, not thousands of years. Earth's rotation has handled rapid changes before, but the speed of the current forcing is at the edge of what the geological record shows as normal variability. The ancient rocks are not alarming in isolation. They are alarming in comparison when you place the current rate of change next to the historical rate and notice that they don't look the same. There is one final piece of this story that ties the ancient record to the present and to the future. Something that the slowdown of Earth's rotation is doing to a system that every living thing on this planet depends on. Something that connects the spin of the planet to the air you breathe, the food you eat, and the weather you experience every single day. Everything you know about weather begins with rotation. The Coriolis effect, the deflection of moving air and water caused by the spinning planet, is not a minor correction to atmospheric physics. It is the organizing principle. Without it, air would flow directly from high pressure to low pressure and stop. With it, air curves, spirals, organizes itself into the enormous rotating systems that carry heat, moisture, and storms across continents and oceans. Hurricanes exist because of Earth's rotation. The trade winds that defined ocean navigation for centuries exist because of Earth's rotation. The seasonal monsoons that bring rain to billions of people across South Asia, West Africa, and Central America exist because of Earth's rotation. The ocean gyres that distribute tropical heat toward the poles exist because of Earth's rotation. All of this emerges from the spin, from the simple fact that the surface beneath the moving air is itself moving, faster at the equator, slower toward the poles. So, when Earth's rotation speed changes, the Coriolis effect changes with it. Confirmed research has shown that during past periods of faster or slower Earth rotation, identifiable through the geological record, global climate patterns shifted measurably. The strength of tropical circulation, the position of storm tracks, the intensity of monsoon seasons, all changed in correlation with rotation. Scientists are careful to note that the rotational changes currently being measured, milliseconds per day, are far too small to directly reorganize weather patterns in the short term. The dominant driver of current climate change is atmospheric composition, primarily greenhouse gases. This is confirmed. The rotation contribution to weather right now is real, but small. What makes it worth understanding is the longer game. If Earth's rotation continues to shift over decades, the cumulative change to the Coriolis effect becomes more meaningful. Storm tracks shift, monsoon timing drifts. Models projecting climate conditions a century out have to account for it. There's also a connection most people never consider. Many species, birds, sea turtles, whales, salmon, navigate using magnetic field sensing and gravitational cues. The magnetic field is generated by the same core that influences rotation. The current rotational changes are far too small to affect any living species today, but it is a reminder of how deeply embedded Earth's spin is in the fabric of life on this planet, woven into biology over hundreds of millions of years of evolution. The rotation of this planet is not a background detail. It is the engine of the atmosphere, the shaper of oceans, the organizer of weather, and the ancient rhythm that every living thing evolved alongside. Change it enough, over enough time, and you change the conditions that everything on the surface depends on. And it is changing, right now, being pushed by forces ranging from invisible iron currents 2,000 miles underground to the irrigation systems of human agriculture. All of it registered, second by second, in atomic clocks and satellites, watching a planet in motion. What comes next depends on choices that are still being made. Science is most useful not when it describes the past, but when it helps navigate the future. And on Earth's rotation, the models are now detailed enough to make some projections with reasonable confidence, alongside clear acknowledgement of what remains uncertain. Here is what confirmed science projects, based on current trends. In the near term, the next few decades, Earth's rotation will likely continue to be variable. The atmosphere will push and pull with seasonal and year-to-year variations. The core mantle coupling cycle may shift toward a phase that gradually slows the recent acceleration, though the exact timing is unknown. Ice loss will continue and likely accelerate. Greenland and Antarctica are both committed to ongoing mass loss based on the warming already locked in. That mass redistribution will continue to push on the rotation for decades, regardless of what happens next. Post-glacial rebound will continue for thousands of years, regardless of what happens to current ice. The land is still rising. That signal will remain in the rotation data long after every other human-caused change has either stabilized or worsened. In the longer term, centuries to millennia, the models project a gradual slowing of Earth's rotation, driven by tidal breaking from the Moon and the growing ice loss redistribution effect. Days will get fractionally longer, not in any way you'd notice in a lifetime, but measurably in the atomic clock record, year after year. The wild card is the tipping points. If the West Antarctic ice sheet begins significant irreversible retreat, or if the Greenland ice sheet crosses its self-reinforcing melt threshold, mass redistribution would accelerate beyond current trend lines. Models including these scenarios show more dramatic rotational changes. Which future plays out depends on emissions and warming timelines that are themselves uncertain. There is one projection that almost all models agree on, regardless of scenario. The variability in Earth's rotation will increase. The swings between faster and slower periods will become larger and less predictable as the forces driving them become more energetic. A warming atmosphere holds more energy. More energetic weather means stronger atmospheric angular momentum signals. More ice loss means more rapid mass redistribution events. The rotation won't just change, it will change more erratically. For the systems that depend on precise timekeeping, GPS, global communications, financial infrastructure, that increasing variability is the operational challenge, not the average change, but the unpredictability around it. And for the scientists trying to understand it, the challenge is the same one that has defined this entire story. A planet made of interconnected systems, each one pulling on the others, none of them operating in isolation. Understanding what Earth's rotation will do next requires understanding everything that is happening to everything else simultaneously. That is hard. It may be the hardest scientific problem that directly affects everyday human life, and yet the tools for solving it are better than they have ever been. The satellites are sharper. The seismometers are more sensitive. The models are faster and more detailed. The global network of monitoring stations is larger and more coordinated. The planet is not hiding what it's doing. It is broadcasting it, continuously, in signals that scientists are learning to read with increasing clarity. What those signals say about the future of this planet and of the days that every person on it lives through is the most important question the data is being asked to answer. Here is what you now know that almost nobody else walking around today understands. The day is not a fixed thing. The 24 hours you woke up inside this morning is not the same length as the day your great-grandparents woke up inside, or the day a person living 2,000 years from now will experience. It is longer than the day a dinosaur lived through. It will be longer still when Earth is old. The spin of this planet is alive. It breathes with the seasons as the atmosphere expands and contracts. It responds to storms. It registers earthquakes within minutes. It adjusts when glaciers melt, when groundwater is pumped, when the liquid iron 2,000 miles beneath your feet shifts its flow. Every layer of this planet is in conversation with every other layer. The core speaks to the mantle speaks to the crust speaks to the ocean speaks to the atmosphere speaks to the ice, and the ice speaks back to the ocean, to the crust, and eventually to the core, a planet-wide system of feedback running continuously for 4.5 billion years. You are living inside one moment of that conversation, a moment that happens to be unusually dynamic, unusually fast-changing, a moment when human activity has added itself to a set of forces that were already in motion, pushing on a system that was already sensitive. The atomic clocks noticed, the satellites noticed, the researchers who stare at rotation data every day noticed, And now you notice. The honest summary of where science stands is this. We know Earth is spinning faster right now than it has in decades. We know the main reasons: the core, the ice, the atmosphere, the oceans, the moon, and human water management. We know this acceleration will not last forever. We know the long-term trend points towards slower days, and we know there are signals in the data that the models don't fully explain yet. What remains genuinely open is when the current acceleration ends, how fast ice loss will progress, whether tipping points will be crossed this century, what the unexplained residuals in the rotation data are telling us, and what discoveries are waiting in the still poorly measured parts of this system: the deep ocean, the core mantle boundary, the terrain beneath Antarctic ice. Science is not finished with this question. It is barely past the beginning. But here's what is not uncertain. This planet has been changing since the moment it formed. It changed when a Mars-sized body hit it and gave it its spin. It changed through billions of years of tidal slowing. It changed through ice ages and volcanic winters and asteroid impacts. It changed as life evolved and altered the atmosphere. It is changing now. Earth does not sit still. It never has. It is a system in motion, always adjusting, always responding, always becoming something slightly different from what it was. The day you are living through right now is 1.59 milliseconds shorter than it was 50 years ago. You cannot feel it. You will never feel it. But it happened. It is real. And somewhere, in a basement lab in Colorado, an atomic clock is counting every moment of it, patiently, precisely, keeping time on a planet that refuses to hold still.